So we're going to finish our discussion of electric potential by talking about how we can connect the electric field to the electric potential. And one way we'll do this is to use what's called an equipotential surface or line. And this is a line or a surface where all the points have the same potential. And there's two rules about how you can connect these equipotential surfaces to the electric field. The first is the surface must always be perpendicular to the electric field at all points. And this is so that the E field can do no work if your charge is moving along at the same potential. Another rule is the electric field points towards lower potential. Rule of thumb there is that electric field points downhill. Now let's see how this works, and we'll use this same example of a capacitor and then a building. And so they work very similarly. These potential heights here are very similar to the different floors in a building. So the first rule is the electric field has to be perpendicular to the equipotential surface. You can see here that the electric field is 90 degrees to these little blue lines. And so the idea is if I'm over here at, say, the 30 volt height and I slide a positive charge over to 30 volts, I'm not going to change my potential energy because my volts isn't changing. And so therefore the electric force can't do any work. And so that means it has to be 90 degrees there, so it can't be sort of helping or hindering that motion. Now, as far as the pointing downhill, we can take a positive charge. Now, we've discussed before that if I take this positive charge, so here it's about near the 20 volts, if I want to increase its potential energy, I'm going to bring it over here, okay, to a point closer to the positive side of this capacitor, so it's got more potential energy. Now, in doing this, if I look at my equation, the change in potential energy is Q. Now, this is a positive charge, so it would be positive. So if I'm going to increase my potential energy, I've got to increase my volts to do that. And so we know that if to go from this point to this point is how I increase the potential energy, that must be an increasing potential. So it must be increasing in that direction. So the general rule, like with the capacitor here, is the positive end is the higher end, and then the negative side would be the lower end. And here I decided to call the bottom, 0 volts. Now it can be helpful to use a quantitative relationship here that can sometimes better encapsulate some of these things we've been talking about. And so here is the electric field in terms of the potential. So the electric field, the three components that we might have, the electric field in the x direction is the negative of the derivative of the potential with respect to x. And so this is an equation that we can use to sort of see, again, better this relationship between the field and the potential. And then one thing is sometimes if you've got delta x, if your delta x is very small, sometimes you can approximate this derivative as just delta v over delta x negative. So again, that's an approximation, but it can be handy, again, to sort of understand some of this stuff conceptually. So here's our good old friend, the capacitor. So we got 60 volts at the top, 0 volts at the bottom, and let's just go ahead and call this axis here to be the y-axis. And so if I do a side view, so sort of take my eye here and look from the side, I'll get a picture kind of like this. And you see that basically it's just this decreasing line from 60 to 10. And so we take our new relationship. The component of the electric field in the y direction is the negative of the slope of the potential versus y line. And so you can see here that the slope is just a nice steady value down like this. And so the electric field, again, points from 60 to 10, which is what we have here and what we've been talking about already. So again, the sort of idea, the electric field points downhill. And what this means is the positive charge wants to move downhill, right? The positive charge, if you put it somewhere, it's going to feel a force in the direction of the electric field. And so if I put the positive charge right here, it's going to feel a force down in the direction of the electric field. One thing is that, too, is that for a capacitor, this approximation of delta V over delta Y is exact because the slope of this line is the same. It's just delta V over delta Y. So that's an exact relationship for the electric field inside a capacitor. So speaking of which, let's try an example. A capacitor has a plate separation of 0.2 meters. If the voltage difference between the plates is 50 volts, what is the magnitude of the E field halfway between the plates? So think about this one and we'll talk about it. All right, hopefully you got C. And so again, as I was saying, we can just use this relationship here for the capacitor. So electric field is delta V over delta X. Now, I just got rid of the negative sign because in this case it doesn't really matter too much to us. And so I want to find the electric field, and now it's going to be the change in volts. So if I drew my little picture of the capacitor, so maybe here's my positive side, and then here's my negative side. All right, so I know that the difference, the delta V between these two plates, is 50 volts. So my delta V is 50 volts, so I know that. And then they're told that the separation distance between them, let's just go ahead and call this axis the x-axis maybe, is 0.2 meters. And so I take 50 volts and divide by 0.2 meters, and I get 250 volts per meter. Now, one thing just to note, this idea of halfway between the plates, well, the electric field is constant between the plates, and so it's going to be the same no matter what position we try to measure it at. All right, here's another example question. At which point is the electric field stronger? And we're given a plot of the potential versus x versus position, and we're interested in these 2 points, x sub a and x sub b. So think about this one and let us know what you think. All right, I got x sub a, so let's look at this. So basically we know that the electric field in the x direction is the slope of dv, or dv dx, which is the slope of this plot at position x. And so if we look at the slope here, so the slope here is something kind of like this, okay, excuse the drawing, and the slope here is much less steep, something kind of like this over here. It's not exactly flat, but it's getting kind of close. Now the thing is, here we're asked which one is stronger, and so really we're just looking for the derivative with respect to x. So which one is a stronger field? So the thing is this one would actually be more negative because of this negative sign. Okay, so it's a positive slope, it'd be more negative, but it's going to be a stronger actual electric field than this one. So this one here is very close to 0. This one's going to have some non-zero value. And then just a couple words about equipotential lines. So we've looked at these in the case, a few different cases, but basically they're very similar to a topographic map. So kind of a map like this where you have the heights are sort of established by different lines. And so every sort of connected line, every connected circle is a different height. And so that's the same thing that works with electric potential. And so here we have sort of a three-dimensional representation of some electric potential. Now the way that this works is the peaks of the potentials will generally be positive charges and the valleys will be negative. And so here's a nice 3D picture. Now if you look sort of from above, you can get a picture like this. And so you often see a picture sort of like this sometimes. And again, it looks like a little topographic map where there's 2 peaks and 1 valley. So this little plot here is basically a cutout from this little section right here. And so you see that initially you come to a valley, and then over here you come to the peak. And so you can do different things with a picture like this. One thing is, suppose I have, a charge right here, a positive charge, say, and I want to know what the direction of the force is. Well, it's kind of hard to know exactly what's happening, but if I look at this, the electric field has to be, as we know, perpendicular to that surface. And so it's going to be perpendicular to this equipotential line, and it's going to be pointing downhill. And so this is 20 volts, and so it's going to be pointing this way. So we can actually figure out the force, because I know this is the electric field, and so the electric field is in general the same direction as the force for a positive charge. So you can do a lot from a picture like this. And here's another question dealing with these kind of topics. So an electron is released from rest at x equals 2 meters in the potential shown in this picture, again V versus x. What does the electron do right after being released? And so there's a bunch of options there. And so think about this one, pause for a second, and we'll talk about it. All right, so I got moved to the left with increasing speed. So let's talk about this. So first, it goes back to our equation. The electric field at x, okay, at this particular position is equal to the negative first derivative of potential versus position. And so right here, now again, we're not looking at the value of the potential, we're looking at the slope. If I look at the slope, it's some nice negative value. Okay, I don't know what it is, but it's some negative slope. If I wanted to, I could try to figure it out from the graph, but it's not really important to us. So it's a nice negative slope. So the actual dV dx at that point is negative, so overall the electric field is positive. So the positive is the electric field. So what that means is that if I put a positive charge here, it would get pushed to the right. However, we're talking about an electron here. So an electron wants to do the opposite. So if it's a negative charge that I'm putting here, it wants to go against the electric field. So it's going to feel a force to the left. Okay, so it has to be one of these answers here to the left. And then the next part, the increasing speed. Well, since the electric field, basically if you look right here for this moment, it's pretty much a nice constant slope. So the electric field is a nice constant value, and so the magnitude of the force equals Q times electric field. So I'm going to say that our force, the magnitude, is basically a constant at this point. Okay, you can argue that later on it'll change a little bit, but right at that point it's about a constant. And either way, there's going to be some non-zero force because there is a slope there. And so because there's a non-zero force, if we just do F equals ma, the acceleration, there will be an acceleration. So it'll be increasing speed. So a rule of thumb you can use for pictures like this and for questions like this is that in general, a positive charge with a plot like this is going to want to go downhill, which is maybe what some of you had expected with this one here. A negative charge is going to feel a force or want to go uphill, which is kind of very counterintuitive, but because we don't have some sort of like a negative mass, we don't have any experience with that. Finally, I just wanted to sort of talk and connect this to the idea of a battery, which is something we're going to be using a lot in the next couple of weeks. So we're going to talk a lot about electric circuits. An electric circuit generally transfers energy from a battery to some device. Maybe it's a radio or a light bulb or a computer or whatever. And so a battery is an object that transforms chemical energy, usually, into electrical energy. And basically this is more chemistry, but there's chemical reactions that transfer electrons from the positive side of the terminal to the negative side. And this gives the terminals a potential difference. All right, and so a picture I can sometimes, I'll sort of show, is there some sort of mechanism. Okay, now we know it's chemical, but you can kind of imagine it's like a little, maybe there's a little conveyor belt in here, and that conveyor belt works to take negative charges from the positive side and moves them over to the negative side. So you have a bunch of negatives here, a bunch of leftover positives here, and so if you were to say connect a wire between the two, you have these electrons that are really excited to go through the wire and get to the other side. And that's sort of the idea of a battery. And as if you do hook up this battery and it does use electrons, the battery has this conveyor belt to move the electrons back over. And again, that's generally done with chemical reactions, but it's a nice little picture, I think, to think about the conveyor belt there.